would like to thank the organizer for asking me to give a course in topos theory, that course that I share with Olivia. We had some discussions, Olivia and me, on what to do. I sort of insisted to try to give the big picture of topos theory, because I think topos theory has evolved quite a bit since its creation by Grothendieck and his students, and maybe it's time to understand what's going on. I will be separating my course in 3 parts. There are 4 hours. So it's a bit of a problem because it's difficult to divide 4 by 3, and but I will do my best. I will start with the theory of locales. So I will spend this first hour and a fourth with the theory of locales, and then I will begin with topos theory for the second part. I will do again some topos theory tomorrow, and I will finish with higher topos theory. Well, it's a bit presumptuous of me to believe that I can actually describe these 3 theories in 4 hours. So I will just make some kind of sketch, and sometime I will give proof when the proof is really easy. If the proof is a bit difficult, I will just maybe discuss the idea of the proof. The theory of locales was invented in the 50s, actually. Charles Ehresmann introduced the notions of locales, and many of the things that happen in topos theory can be actually already seen in the theory of locales. So the theory of locales is a good start for topos theory because it's very elementary. It's quite elementary. It's much simpler than topos theory, and many of the phenomena that happens in topos theory can be seen there. And if you know the theory of locale, sometime when you learn topos theory, you say, "Aha, that's something I know with the theory of locale, and it's just the same thing." And so I'm very much, when learning a subject, very much on the idea that the bottom-up approach, not the top-down. So unfortunately, books in topos theory now, they start straight with the topos theory, and they give a chapter, maybe chapter 9, chapter 10, the theory of locales. Okay, so I very much recommend, if you read these books, to go straight to the theory of locales, maybe chapter 10 or chapter 9, and then start to read the beginning. Maybe a little bit of philosophy to start, to begin, about geometry and algebra. Well, algebraic geometry is precisely the subject about the interaction between geometry and algebra, and we know that somehow a lot of what we call geometry, at least so-called commutative geometry as opposed to non-commutative geometry, is about studying rings, commutative rings. And let me just look at this a little bit to start. So suppose that X is a space, and it's we often sort of understand or study the space by looking at maps from X to some ring R. R itself is a ring object. It's a ring space, if you like. It's a ring object in the category of spaces. Whatever category of space you have. And why do we study maps from X to R? Well, that's historically, this is how things happen. You want, for example, to describe subspaces of X by using equations. So you take so this is a map F. So you take many of them, F1 to Fn, and you describe the equation. So you look at 0, the inclusions, and you pull back, and you get a sub-object or a sub-manifold or a sub-algebraic variety by describing sub-object by equations. So this is a big discovery. I guess this is due to Descartes, that somehow a lot of what we think of the geometry is completely understood by or maybe described by the algebra of functions or something like that. Now, so if you have a space, you look at the maps from X to the ring, and this itself is a ring. So this gives you a functor from, let's say, map X R from spaces to the category of rings. And very often you can describe some kind of adjoint, which maybe you could call this the spectrum. So that you will have then a bijection between, let's say, if you have a ring A, then you have the spect of A, and there is a bijection between the map from X to the spect of A, and the ring maps from X into map XR. I hope I'm getting it right. Okay. Now, this duality between the rings and space does not work perfectly, in the sense that very often it's not an equivalence. So when it is not an equivalence, we try to improve it, either by extending the class of rings you consider, or by extending the class of spaces, trying to adjust the two sides. So there is a kind of dialectic. You have notions of space, a notion 0 of spaces, and the notions 0 of rings, and you have a functor, maybe some kind of adjunction between the two, and you want to transform it into an equivalence, and maybe you extend the notions of rings for that. So you have a notion 1, and this leads to a notions of space which is a bit more general, space 1. And again, these things do not fit completely, so you extend one of the two sides to make it, and it keeps on like this. And I don't know what is the end result. I mean, it seems that in mathematics we have been doing that 6 or 7 times, and it keeps on. So maybe I will first start with the examples of locales. In the case of locale, the spaces are just the topological spaces. So I will write this top for the category of topological spaces, topological. And the ring, in this case, could be taken, of course, the complex to be taken to be the complex numbers, the real numbers, but you one also has the choice of taking the Sierpinski space. So the Sierpinski space has 2 points, let's say 0 and 1, and the open of S is you have the empty, you have let's say 1 is open, and 0, 1. And the nice things about the Sierpinski space is that if U is an open subset of a space X, maybe I should write it like this, U an open subset, then there is a unique map, continuous map from X to the Sierpinski space, such that the following square is a pullback. I take 1 here. So this map here is called the characteristic map of the open set. If X is in U, 0, otherwise. And so there is a bijection between map of X into the Sierpinski space and the open set of X. And so mapping topological space into the Sierpinski space gives you all the information about the open subset of X. So the idea of the theory of locale is to concentrate on the sort of ring that the open set of X constitute. So so what are the operations on the Sierpinski space? If you, for a general ring, I mean, we are interested in operations. The basic operations for a general ring are addition and product and multiplication. So what are the operations that exist on the Sierpinski space? Well, general operations, well, I can give you a couple of them. Maybe I should write just S. 0, 1 is a poset. So you can look at suprema and infima on this poset. So that gives you, for example, the supremum of 2 things will give you an operations, and the infimum will give you another one. And these 2 operations behave very much like sums and times. You have, for example, the distributivity law. Of course, you have much more relations, many more relations than just distributivity law. But also, you can consider infinite operations, because you can take infinite powers of the Sierpinski space. It's also a topological space, just the product topology. And you can consider continuous maps from S to the I to S as basic operations on open sets. And one of them is just suprema over I. The suprema over I of a family Xi is just what it is. It's the supremum of the xi. So the supremum over I actually always produce 1 unless the sequence that you have here is completely 0. And this operation is actually continuous. And this is the basis of the theory of locales. So a locale can be defined to be actually it's called a frame, because when we talk about locales, we are really talking about a ring. So actually, let me draw the picture. You have rings, schemes. So we know that there is a kind of duality between rings and scheme. And here I'm going to put frames. This is a kind of ring-like object. And here to put locales. This is just like the opposite category. The category of locales will be the opposite category. So what is a frame? So the definition is that a frame is a complete lattice. Maybe I will describe what is a lattice in a moment, which is such that the distributivity law distributivity law holds. In this equation, it's important to observe that the infimum, which is called the meet, this is the operation here is called meet of x and y, is distributive over arbitrary suprema. And this is very important for the notions of a frame, and this notion was introduced by Ehresmann, I think. RSS. Ah oui, pardon. Excusez-moi. Voilà. Thank you. So the first example of a frame is, of course, the lattice of open subset of a topological space. And maybe I should say what a lattice is. A poset P the L is a lattice if it is a complete lattice if it admits suprema arbitrary suprema and infima. So that's the notions of a lattice, and it's important to observe that it's enough to have suprema or infima, because the infimum of a subset. So if you have a subset S of the lattice L, you can express the infimum as the supremum of the set of lower bounds. Of S. So that's an important observation, which is of course well known. So for example, the lattice of open subset of a topological space is closed under suprema, because the suprema is the union, the supremum of a family of open set. So OX is a frame. The supremum of a family of open set, of course, is the union. But this lattice is also complete. I mean, it has an infimum too, and the infimum of a family, of open set is just the intersection, and then you take the interior of the intersection. Okay. So we see here that the infimum has a kind of weird, apparently weird description, because you need to take the interior. And this is why the opposite OX up is not a frame in general. That is the distributivity of a union over intersection, which exists in the power set. I mean, there is a distributivity also because of the Morgan law. Does not survive when you look at open set. So the opposite of a frame is not a frame. And a map of topological space give you a map in the other direction, which we could call F upper star, just the inverse image map. And if you look at the properties of this map, is that it is a morphisms of frame. Now, by morphisms of frame, I mean a map, so you have two frames, A and B, so phi and A and B. It is a map which preserves the operations, arbitrary suprema, and a finite infima or meet. Okay. And we should not forget that there is a unit element for the meet, which I will write 1, which is the top element. So 1 in the case of a frame is X itself, is the unit element for the intersection. So this is how the notions of morphisms of a frame, morphism, is defined. And it's straightforward to check that the inverse image map is a morphisms of frame. So So you get a functor from the category of frames. I will write FRM for the category of frames in morphism, and you get a functor that goes in this direction, maybe from top, and let's call it O. It's a contravariant functor. Maybe a word about the terminology here, because some people say that a contravariant functor they say that this is a contravariant functor, right? I'm sorry, this is a covariant functor, because it's okay. So covariant functor from the covariant functor is the same as a contravariant functor from C to D. Contravariant. So when you say that a functor is contravariant, you don't need to write up, okay? So because I prefer to do things like that. And also for posets. I mean, if you have a map of posets, and I will use that, F, map of posets, I mean, it's called preserving the partial order. You have two versions, a contravariant and a covariant one. And so if I want to say that a map between two posets is a map of posets, I would say it's a covariant map or a contravariant map. There are two possibilities. Okay, so here you have a contravariant functor. It turns out that this functor this contravariant functor has an adjoint which associate to a frame a topological space, the topological space of its point. So essentially, the points of a frame topologize. It's home in the category of frames of A into the initial frame. So by bracket 1, I mean this frame with two elements, 0. This is a frame. This is bracket 1 is actually O of a point, and you define the notions of a point of a frame by looking at morphism from the frame to 1, and you get an adjunction between two contravariant functor. Maybe I should write explicitly the form of the bijection. So so if you have X a topological space and A a frame, then you can look at OM of A into OX. So this is in the category of frames, and this will be in bijection with the continuous map from X to the space of points of A. Topologize. Okay. So there is an adjunction between these two categories, but the adjunction is not an equivalence. There are more objects here than there are topological spaces. Actually, there are frames that don't have any point. So this is why the theory of locales has been called sometimes pointless topology, because the points in a locale are not that important in the theory of locales. They are important, but some locales don't have points, and they are important in the theory. So I will, maybe I don't have really time to discuss examples, but I just tell you that some locales don't have points. Okay. Okay, so how does it work, the theory of locales? Well, a frame. Oh, I forgot to tell you what a locale is in this picture. The locale is just an object in the opposite category of the category of frames. So locales don't have existence except by being a frame somewhere. So this is kind of a fiction. The notions of locale is a fiction. The reality is that what you have is a frame. But this fiction is very important when you think about the theory. You want to have intuitions about the space that you're looking at, and so we often look into the opposite of the category of frame. It's a little bit like in algebraic geometry. Sometime in the theory of rings, it's very good to think of a ring as an affine scheme. And so we, but in this case, there is an actual general notions of a scheme, which is partly independent from, well, not exactly from the theory of commutative rings. So, so this functor here, which was contravariant, once you use this duality, you get actually a pair of covariant functor. If you change the covariance, if you replace frame by locale, what you get here is two covariant functor. Yes. Well, in principle, they are defined here. We could call that a character, you see, of the locale. The locale is like a ring, and this is like the base ring. And you look at homomorphism from A into the base ring, and in representation theory, this is called a character. So a point of locale is a character. Maybe I could say a little bit about it, because yes, right. But maybe I can say a little bit about the notions of a point of a locale by looking at the homomorphism, a character of a frame. So a character needs to send the element 1. You see, it must be the characteristic functions of something. Here there are only two values possible, okay? So it must be the characteristic functions of something. It sends the elements 1, the top element here, to 1 by notions of a morphism. A morphism frame sends the unit to the unit. So the only thing which is interesting in the morphism is the kernel of phi. Now, this kernel is closed under suprema, because if you phi is closed under, I mean, respect suprema, so the kernel of phi is closed under suprema. So you can take the union of everything that is in the kernel. So let's call that K of phi, the supremum of all x in the kernel of phi and x. So this is the maximum element in the kernel. And if you know this maximum element, you know everything about the character. And so you may think of this as an open subset of the space. So this is open. Open in the sense that in the locale, it's an open thing, okay? So what is so special about these open sets is that they are meet irreducible. So if I call U the K of phi, the maximum element in the kernel, U is meet irreducible. And this means what? This means that if you express U as the union of two other elements of the frame, then it must be that U equal to U1 or U equal U2. So that's, I'm sorry, meet, yeah. Thank you. And two, you need that U is different from 1, okay? This is called a meet irreducible open set. Where does this property comes from? It comes from the fact that this morphisms of locale respect intersection. If you just play with the axioms, you discover that the element U here is meet irreducible. So the complement of U, which normally should exist, is a closed sublocale. I said nothing about closed sublocale. The complement of U, which is the closed part of A. This is just the A up, actually. There's a lattice of closed subobjects in the locale. This is just the opposite lattice, okay, is joint irreducible. So it's a joint irreducible. So joint irreducible means that if F is F1 union F2, then F equal or F equal F2. So there are two conditions, and the other is that F is not empty. So there is a bijection, if you like, between the points of a locale and the irreducible closed subobject of the locale. So that's one way to understand what is a point. And in a topological space, if X is a topological space, then if you take an element X of the topological space, and then the closure of the singleton is irreducible, is a closed irreducible. So that's the connection between the classical notions of point of topological space, is that the morphisms of locale, they produce closed subobjects that are irreducible. And I don't know if this answered the question. Okay. In a topological space, right? This is true. Yeah. That's an example of closed irreducible, but there are in a topological space sometimes closed irreducible that don't have a generic point. This is called or a generator. Okay. Yeah. Okay. Now. Okay, so what I want to develop here is the fact that frames are rings, and really, I mean, I'm serious. I mean, frames are rings, in the sense that the theory of frames is very much like the theory of commutative rings. So, but somehow it is simpler. It is simpler. It's a kind of simple versions of the theory of commutative rings. the category of frames is an algebraic category. In a sense, it's like the category of groups, or the category of rings, or the category of abelian groups, the category of Lie algebra. Universal algebra applies. So what does it mean? I mean, for example, if you have a morphisms of frame, you can decompose it into three morphisms. Should write 5 there. Like in the theory of rings or whatever, okay? First, you take the image of the morphism, you get here a subframe. That's the notion of subframe. There is an equivalence relation on A defined, like the usual, a congruence. There is a notion of congruence in the theory of frames. Okay, what is the congruence in the theory of frame? It's an equivalence relation. It's an equivalence relation. An equivalence relation is always a subobject of the product, but it should be a subframe of the product. That's all. Okay, an equivalence relation is a congruence if it is a subframe of the product. So it tells you everything about the congruence. So given the morphisms of frame, there is a congruence, which I write here as an equivalence. So you can take a quotient to get a frame, and then here you have this as a morphism. So in other words, there is a notion of surjection in the frame, and the compositions of every map as a surjection followed by an injection, injective morphism. Okay. Well, for the theory of locales, it means something. In the theory of locales, you reverse everything, so you have a continuous map, f from x to y, and the injection here becomes a quotient locale. Okay, let's call it z, a quotient. So what is the notions of quotient locale? The notions of quotients locale comes from the notions of subframe. That's just straightforward reversing. And the quotient frame leads to an embedding. Let's say here, this is embedding of locales. So every morphisms of frames has a decomposition as a quotient followed by an embedding. Okay. Except that in the theory of locales, something simpler is happening, because a map of locales, morphisms of locales, let's say 5 from A to B, has a right adjoint. In the category of poset. The right adjoint is not in the category of locale. The right adjoint is not a morphisms of locale. It's just an order preserving map, or a covariant map between two poset in the category of poset. And this is just this follows from the fact that phi preserves suprema. Any map preserving suprema between two complete lattice has a right adjoint. It's I'm sorry. Which I will write phi lower star from B to A. Oh, I'm sorry. I confused myself. Of frames. Yeah. Okay. Okay. And the existence of this right adjoint makes things simple about this decomposition, because it's a general theorem of category theory, that if you have two poset, P and Q, and let's say a map this way, let's say F, and another map the other way, let's call it G, okay, and I'm supposed that F is left adjoint to G. That means that f of x that we have this equivalence. Then this is well known. You can compose f with G. So you have compose with G and call it sigma. This is a map from sigma. This is a map from P to P. This is a closure operator. On P. So closure operator means that it is, of course, equivariant, yeah, order preserving. So you have and that you have sigma square of x equals sigma x, and the composite the other way, Fg, let's call it a rho, which is goes from Q to Q, is I call that a comonadic operator. It's the dual of being a closure, because a closure operator can be called also a monadic operator. So a comonadic operator is just a dual. It's an order preserving operator that satisfy and and you have the compositions. If I look at the set of sigma closed things in P, and Q rho as the row open elements, if you like, or that's the fixed point of rho, then you have the composition of F has a map first to P sigma, another to Q rho, an inclusion here, and here an isomorphism. That's you have the compositions like this, and there is a similar decomposition the other way for G. So for G, you have an inclusion, P sigma, an isomorphism, and Q rho for the fixed point. I mean, in sometime in abstract Galois theory, the certain thing could be called a Galois connection. And if you have a Galois connection, you get a bijection between the closed things on the two sides, and that's really no more than that. Now, that's why I call that monadic and comonadic, except that in the situations of having two categories and two functors like this, you have a monad and a comonad, and this decomposition, there is a decomposition, but the middle terms is not an isomorphism in general. So that makes things more complicated. It happens that To make it short, in the case of a homomorphism of phi between two locales, so I will write phi like this, and you have the right adjoint phi over star. Then, if you compose phi over star and phi this way, you call it sigma. It's an operator from A to A. But in addition to the conditions that I wrote for the closure operator, it preserved meets. Simply because phi it's in a homomorphism of French, so it preserves meets by definitions in a homomorphism. And phi over star, being a right adjoint, always preserve intersections, so the closure will meet. So an operator, a monadic operator, which preserve meets, is called a nucleus in the theory of frames. In the theory of frame. And there is also a comonadic operator, which preserve meets for the same reason. I'm going to call it a co-nucleus, but I have not been able to check with people developing the theory of frames if this is the standard name for this notion. But I wasn't going to call it a co-nucleus. It seems to be a reasonable name. And then, if you have a nucleus, you could look at the fixed points, and I'm going to call it A sigma. And the fixed point of a nucleus form a locale. It's a poset, it's a locale again. And there is a quotient maps that send x into sigma x, the closure fix. You see? So A sigma, the fixed point, is a locale. And this quotient map Q is a morphism of locale.
Is it a frame or a frame?
Thank you for. Yes, thank you.
From the beginning.
So it's a quotient frame. Thank you. Okay. Maybe I should just stress the fact that this is not a sublocale of A. This is a quotient locale. I mean, in the sense that the union here is not the usual union, because the union of closed things is not closed. So in the union here, the union of a family of closed elements, union with respect to sigma, okay, that's a closure of the family. So this is not a sublocale, but this A sigma is of course included in A because by definition it's the set of fixed points. So, but the inclusion is the right adjoint to Q. Okay, but the inclusion does not preserve union. However, the quotient map, the quotient map is a morphism of frame. A sigma is a subframe of A.
So, in the context of topological spaces, is it so when you have a subspace of a topological space, is it a situation what you consider that the frame of opens in Y is obtained like this from the frame of opens in X?
No, we should not, I don't know if I understand your comment correctly, but we should not think of sigma as like the closure of the usual closure on the subset of a topological space, because the usual closure operator does not preserve intersection. The interior preserve intersection, but not the closure. Okay.
No,
So okay. So this is really what people now call a group-D topology. This is what a group-D topology is. A group-D topology is exactly exhibiting an operator like that on a frame which preserve meets. And this is like the sheaves with respect to the group-D topology. Okay. So and on the other side, you have B rho, the fixed point of the of the co-nucleus. And now the inclusion is, this is a frame, and the inclusions is a map of frame. This is a subframe. The inclusion presents the union, and there is an isomorphism between the two, just induced by the map phi. Okay. So there is a theorem here, which is that there is a bijection between the quotient frame of a frame A. There is a bijection between the quotient frame and the nucleus. And there is a dual theorem saying that there is a bijection between the subframe and the co-nucleus. Okay, just completely dual. Now, I want to talk about the free frame. If frames are really rings, I mean, there should be free ones. So what are they? Because in commutative algebra, the polynomial ring is playing an important role. So you would like to know what are the free frames. Now, I should say that in commutative algebra, the free commutative algebra on a set of generator is constructed actually in two steps. So you have the category of commutative rings, and you can forget that the ring has an addition, and you get into the category of commutative monoid. So there is a forgetful functor from commutative ring to commutative monoid, where you forget, and you can forget again if you like, and you get into the category of set, so forget. Now, each of these two functors has a left adjoint. First, you can generate a free commutative monoid from a set, and second, you can generate a free commutative ring from a commutative monoid. This one, take a set X, and it could be defined like, I think it's sometimes denoted Xn. Okay, that's a notation, Bourbaki notation, I guess, for the free commutative monoid on a set N. So these are commutative monomials in X. And the second one, you take N something here, okay, and you take the group, actually the monoid ring of it, Zn. So maybe I should write it like this. So the free commutative ring on a set can be obtained by combining these two steps. Now, I want to stress the fact, I mean, the first step is just normal, but the second step has something peculiar about it, because Zn is Z tensor N. Actually, it's the free abelian group generated by the set N. You forget that N has a monoid structure. You linearize N, and that's it. This object is an abelian group by construction. Let's say you could denote it Z to the n, if you like. So you take the free abelian group, and then it happens that this free abelian group has a product. We all know that, and this product gives the free abelian group a ring structure, and that's the adjoint of the forgetful functor. Now, this is a situation which happens pretty often in mathematics. It is when there is a distributivity law. You see, there is a distributivity law between the free abelian group functor and the free monoid functor, and if you combine them, you get a distributivity law, or maybe a distributive law. Distributive law. Or a commutation law. If I had time, I could make it more precise. Let's say, think of the free abelian group functor as a functor from set to set, just because I want to see it as an endo functor. So you take the free abelian group functor, and you forget it's an abelian group, you get a set. Okay, and this is an examples of a monad. So it has a multiplication. It's called a monad. And there's a unit. And there is also the free commutative monoid functor, let's say Cm. Again, I forget it's a monoid. I see it as an endo functor of set to set, and you have a monad structure on it. That comes simply because Cm is the composite of a left adjoint with a right adjoint, and you get this monad structure. It's like the monadic and the comonadic operator before. Now, it happens that the composite of Cm, if you compose Cm with ab, that's a monad. Okay? Because this is the free commutative ring functor, and so it must be must have a monad structure. So how is it that the composite of two monad is a monad? This was observed by John Beck. When is it true that the composite of two monad is a monad? Years ago. So you have a category C, and you have, let's say, two monads. And you want to know if, let's say, A composed with B is a monad. So what do you need to get a product on A composed with B? You would need to say, well, I'm going to do that. I want to exhibit a map like this from the multiplications of A and the multiplications of B. But compositions of endo functor is not commutative. So you cannot switch A and B. You would like to switch A and B and replace that by and then you will be in business, because you will be able to use the multiplications on A and the multiplications on B to get back to A and B. But you need a switching operator, and the switching operator will go from BA to AB. And this switching operator, it's a little bit like a Young-Baxter operator, if you like, but it doesn't need to be full. It doesn't need to be fully a Young-Baxter operator. but it's a commutation operator, which is saying that if you were to do this construction the other way around, in other words, suppose that you're by accident, by distraction, you want to construct this thing, and you first take the free abelian group followed by the free monoid. You won't get what you want, right? But you will be able to rearrange everything by, there will be a commutation operator, and this is called a distributivity or distributive law. This is so-called distributive law by John Beck. And I'm sorry? A distributive law is a precise notion. It's not only an operator like this, but it must satisfy some compatibility relation with the multiplications of A and B. Okay, so I don't have the time to write it down. Okay, now in the case of commutative rings, see, there is a distributivity law. And in the case of frames also, there is a distributive law. So in other words, you can construct the free frame in two steps on a poset. So I'm going to consider the category of frames. And I forget that there is an addition. I forget suprema. So we get into lower semi-lattice. A lower semi-lattice has just an infimum operations, finite infimum. You don't have a suprema or general infima, and you have a unit 1. So this is what defines a lower semi-lattice. So you can forget that the frame has an addition, and then keep forgetting and goes into the category of posets. Now, this functor has a left adjoint, which consists into adding finite means to a poset. The construction is very explicit. And this other functor also has a left adjoint. And this left adjoint is very simple because it coincides with the left adjoint from soup lattices. All right, soup lattices for the category of complete lattices and soup preserving maps. And then there is a forgetful functor here, and the left adjoint is, I call it D. D of a poset, P, is the set of lower sections of P. S is a downward, it's called also a downward section, or a cribble of P. So it means that if X is in S and Y is smaller than X, then Y is in S. Okay. Now this poset has suprema. I mean, it has suprema, and it's the left adjoint to the forgetful functor from the category of complete lattices and with suprema to poset. There is a left adjoint, and here it is. You see, this is the same D. So there is. I should finish with that. With the analogy. So we have sets, abelian groups, and commutative rings. Okay, so that's a sequence, and we know that if we want to study commutative rings, we need to study abelian groups first, or modules or something like that. But now we are going to extend that. We take posets. And instead of abelian group, I take soup lattices. And here I put frames. And the category of soup lattices is really like the category of abelian groups. We know that the category of abelian group has tensor product, Hom, and it's additive. The additivity of the category of abelian groups means that the coproduct, finite coproduct, and the product coincide. It's called a direct sum. The soup lattices is the same thing. That's additive, except that here it's even stronger. Any coproduct of soup lattices is also the product. It's very strongly additive. It's the presence of infinitary operations that makes this strongly additive. And it is symmetric monoidal close. And a frame is a commutative ring, is some special kind, actually, of commutative ring in the category of soup lattices. So there is a general scheme here that I think Deling has suggested in a paper that maybe algebraic geometry could be generalized to any situation where you start with a symmetric monoidal category, which is additive in some sense, and you consider a commutative monoid object in there, and they form your ring, and you take the opposite and they form your scheme. And these things just follow this pattern completely. In some sense, we could say that the theory of locale is really like the theory of schemes. But it is... Yes, of course. Yes, that's true. Frame are particular object. That's true. That's true. The general rings here with soup lattices are called quantile. That's they don't need to be commutative, and the commutative one are called commutative quantile. That's exactly true. But there is a nice connection between the two. The inclusions of frame into commutative quantile has both a left and a right adjoint, and it makes life very nice. It's very easy to transport theorems about commutative quantiles to theorems about frame using this adjunction. I guess I should stop here. Thank you very much.